In this lab, the objective is to analyze the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. The results that I obtained were that I got the prediction motion of the mass followed the same pattern as the data received from Tracker. I obtained these results by applying two principles: Newton's second law, or the momentum principle, which predicted the spring's new velocity and position throughout time, and the energy principle, which predicted that the total energy change should be zero, since no energy is being transferred to or from the surroundings with the system choice of the mass plus the spring plus Earth. So I used Tracker to analyze my motion. You can see this here. I tracked the x and y coordinates of the point mass, and I used 0.7 with my calibration stick and put the origin where the spring was attached. I then copied all the relevant x and y values and placed them into a CSV file and loaded them into my Python program. So that can be seen right here into the read CSV, where it's taking this data. Some of the initialized values that I calculated in my Python program, such as at the top, were determined by applying these algebraic rearrangements. I calculated the period t by finding the time that corresponded to two contiguous peak-to-peak minimums in Tracker and subtracting them to find their difference. I then put this value in to solve for the stiffness. So t, 1.16, is equal to 2 pi multiplied by the square root of the mass of 0.402, which is what was given, divided by the stiffness. I found this to be 6.12 newtons over meters. I know this says k sub s, but it's a mistake. It should be like what it is in the mg equals negative ks, where there is a spring constant k and the stretch s. Sorry about that. And then I use the length of the spring in the second equation to find the relaxed length, using the principle of static equilibrium, which means that the net force is zero, or otherwise stated, that the magnitude of the weight force is equal to the magnitude of the spring force. Plugging in the following for the stretch, we can manipulate the algebra until we get a function that solves for the relaxed length. I found this to be 0.0527 meters. So I then loaded this all into my Python program, where I was given the mass, I used my position vector off of Tracker, and velocity starting off at 0, and delta t was also given, where g was given as well. These are the two values that I just calculated over here. This chunk is pretty important. This is the code that calculates the length of the spring at each time interval. L hat is the direction, and J hat is used to calculate gravitational force, and S is the stretch or compression that is used to compute the spring force and spring energy. Then I also have my initial energies that are calculated here, and so I start off my calculation loop, which calculates the gravitational force, the spring force, the net force, which is then used to inform, or rather predict, the ball's velocity, applying Newton's second law, and then that ball's velocity predicts the ball's position next in the calculation loop. And then, of course, we need to update where the spring is, the position, the stretch, and the compression, which is all changed as the mass moves. So, what does this produce when we run the program? So you can see in this display window that the two forces are nearly matched up. The blue line is the spring force and the black arrow is the gravitational force. What I think is the reason why they are not completely aligned is that the drag force is catching up to the spring force, so there is a slight discrepancy. This discrepancy might also be due to the lack of precision of particle mass points when I was analyzing the motion in Tracker. A little frustrating, but not too far away. For the first question, what does it mean? Is the energy principle satisfied? So I calculated the different energy using these equations here, which you saw in my Python program. Notice that for the potential energy of the spring, S is the stretch when it is positive, and it is the compression when it is negative. This graph shows the change in all of the energies. The blue line shows the change in kinetic energy. The red line shows the change in spring potential energy. The green line shows the change in potential gravitational energy, and the yellow is the total energy change. We're plotting with the yellow as the change in total energy, and it should be 0. Technically, the total energy is not 0, but since this deviance from absolute 0 is due to round-off errors, which anytime you use computational tools, this will happen, your final result is prone to this round-off error. We can really consider this negligible, so that means yes, the energy principle is satisfied. And the red and green, is also important to note that they're in phase changes against one another. For question 2, using the data you obtained, make 2 separate estimates of the oscillation periods. So the period of oscillation is different in each. I used a Python shell to calculate for the x and calculate for the y, and you can see there's a difference in 0.08. And that makes sense. They're different because each equation has different values. In the y direction is based on mass and the stiffness, while in the x direction, the calculation is based on the length and gravity. So what this means is that it takes more time to make one cycle in the x direction than in the y direction. Thanks for listening.